All right, so here we are, week 2, August 29th. Tonight we're going to go over chapter 2 of the text. We'll be talking about model-driven test design. Assignment 1 was due tonight. We're going to do our week 2 exercises. A couple of important things coming up on the schedule. Next week, no class, Labor Day. I think that week 3 is kind of awfully early to have a day off. I'd much rather have it in like the middle of the semester, but here we are. So no class next week. And then 1, 2, 3 weeks from now, September 19th, assignment 2 is due. Assignment 2 should be posted now on Blackboard. It may not make a whole lot of sense to you until after we do class number 3, but you are welcome to get started early if you'd like to do that. All right, so typically I will follow up the quick schedule review with a review of either the last quiz or the last assignment or both. Tonight I'm not going to review assignments. Assignment 1 was pretty straightforward, but I will do a quick review of quiz 1. So let's start with the grade distribution, which was unusual. The first quiz is often hard. I was actually talking about this with our TA, and he said, "Oh yeah, I remember the first quiz. I got a 6 on that." And he went on to get an A+ in the course. So I wouldn't worry too much about your grade on this quiz. As I mentioned last week, there are 13 quizzes for the semester, and you're graded on your top 10 scores. So those of you who got a 10, great. Those of you who didn't, well, this will probably drop off the bottom for you. So let's just do a kind of a quick look at the questions here. And what isn't obvious to you as you take the quiz is that there are actually a large number of different quizzes that are out there to the students. Typically, each question has 2 or 4 or sometimes 8 different varieties of it, and then they're kind of randomly selected for your quiz, so everybody's quiz ends up being different. And so I won't go over all of those varieties in detail when I review, but I'll usually pick one and talk about the one and kind of leave it to you to get, okay, I see what happened with that one. Now I understand better what went on with mine. So why is it economical to invest testing effort early? And, we had a couple graphs on this, right? Basically, the earlier we find something, the easier and less expensive it is to fix it. We had some definitions. A fault, right? A fault is a static defect in the software. It's something wrong with the source code. A failure is an observable incorrect behavior of the software. And an error is that thing in the middle. Maybe I should change the order, make it fault, error, failure. That might be more sensible. But an error is some incorrect internal state in the software. And usually that's going to mean an incorrect variable, but it also may mean incorrect control flow, right? The program has branched in a direction that it wasn't intended to, or it's gone around a loop that it shouldn't have gone around, or something like that. And bug, for the most part, is a term that we won't use here because it's relatively poorly defined, although we will end up using debugging as a term. We'll talk about that a little bit this week. And then we get to the thing that was tough. Right, we've got a leap year calculator, and I love this leap year example because it's just complicated enough that you can do interesting things with it while still being pretty straightforward code, right? You don't get all wrapped up in the complexity of it. So it's a great example. It's going to keep on coming back this semester. By the end of the year, you will all be experts in whether any particular year is a leap year or not. So this particular piece of code has a fault in it right here. The fault is that the statement is written as if false instead of as if year mod 400 is equal to 0. So what does that do to our testing? Different people were asked different questions about this code. You all got the same piece of code in the same test cases. You were asked different questions. Rather than address the questions, what I'll do right now is address okay, what happens with each of these? What happens with each of these tests? So do we have any tests that don't reach the fault? Well, 2001 will not reach the fault, right? If the fault is if false, 2001 will not reach that, because when 2001 executes this first line, year mod 4 is not equal to 0, that will be true. So when run against 2001, the function will return false, and this fault will not be reached or executed. Are there tests that reach the fault but don't cause an error, right? Don't cause some problem of internal state? And the answer is yes. 2004 and 2010 both reach it, right? This first if statement is false. So execution comes down to this statement. That's as if false. So execution flows to the next statement. If year mod 100 is equal to 0. However, for 2004 and 2100, that does not introduce an error, because that branching, right, the continuation of execution to this next statement, is the desired control flow for those values. Do we have a test that reaches the fault and causes an error but doesn't cause a failure? And the answer there is no, because anything that reaches the error, right? 2001 doesn't reach. 2004 and 2100 reach but don't cause an error. 2000 reaches the fault and causes an error. The error is the incorrect control flow. It should have returned true, but instead it continued on to the next statement. Because of the nature of the next statement, it will return false when it should have returned true. So 2000 reaches the fault, causes an error, and causes a failure. Okay, so group assignments. Group assignments were made during quiz number 1. It was kind of a random assignment. They did come out relatively evenly. We'll revisit that in a week or two. There are sometimes, I guess I'll say often, there are a handful of people that drop the class in the first couple of weeks for whatever reason. That may, if that skews the groups a little bit, then we may look at having to do some reassignments amongst the groups, just to kind of keep them all on a relatively equal size. So we're going to use these groups for in-class exercises, and only for in-class exercises. You do not have to stay in these groups to do your homework assignments. You can do those on your own. You can do them in whatever group of whatever size you wish, right? So these bugworts, house assignments, that's just for our in-class. There were a few people that did not take the first quiz, so I assigned you into one of these groups where we needed a few extra people. And so we'll get to that later today when we start, after our break, when we start our in-class exercises. We'll break up and into Zoom breakout rooms by these different groups. So where are we on the House Cup? Well, there's not a lot of points involved so far, but here we are. This counts for, let's see, what goes into this? First submittal of the first assignment, the first completion of the quiz, the highest score on the assignment, which was basically all of the groups, the highest score on the quiz, which I think was also all the groups. So there's not much that goes into here yet, but we're off to a relatively even start here. No surprise. All right, that takes us to the end of quiz review for today. Any questions that we want to address here? All right, and let's go ahead and we'll move on to tonight's content. All right, tonight we're going to talk about model-driven test design. So we're going to take kind of some of those things that we kind of just glanced off really quickly last week, and we're going to kind of ratchet up the formality and dig in a little bit deeper here. So software has a substantial, I don't know that I want to say problem, I guess let me say challenge instead, right? Software has a substantial challenge. There is no other engineering discipline that builds things as complicated as software. So if you look at some of the most complex, let's say, mechanical engineering devices, I would argue that probably a modern airliner or a modern spacecraft is, are among the most complicated mechanical engineering devices that are out there. And those things, a modern airliner, a Boeing 787, A300 or A350, I guess is Airbus's latest. They will have some tens of thousands of parts and probably some thousands of parts that are actually moving parts. And if we look at a piece of software, a modest sized piece of software will perhaps have several million lines of code, including hundreds of thousands of decision points, which are, looking at it roughly, somewhat equivalent to moving parts. So software is an order or two of magnitude more complex than the most complex things that are being built in other disciplines. So correctness in engineering really doesn't have a meaning. I mean, if I build a building, is that building provably correct? Is a new car provably correct? Well, no, it's not correct. And actually, no, we can pretty much assume it has defects in it of, some variety or another. Those things are true of software as well. And so like other engineering disciplines, we have to use abstraction concepts to manage the complexity of what we're doing, right? So we can't, as I talked about last week, for any non-trivial piece of software, we cannot formally prove that the software is correct. Instead, we have to make some assumptions, we have to make some abstractions, we have to get the software abstracted to the point where we can test against that abstracted model. And we know that testing can only show the presence of failures. It cannot show their absence. We saw a little bit of that last week where we had an example piece of software, trivial software, but an example piece of software that had a fault in it, but that fault might not get executed, or it might get executed and not cause an error, or it might get executed and cause an error, but the error doesn't result in a failure. So it's entirely possible to have failures in software that are not easily detected. So let's revisit a couple of terms here, or maybe visit them for the first time. So when we're testing, what are we doing when we're testing? And the process of testing is evaluating software by observing its execution, right? We're going to present that software with various inputs. We're going to see what it does. We're going to compare the actual outputs with the expected outputs. That testing may result in a test failure. A test failure is an execution of a test that results in a software failure. And so by software failure, what we mean is an observable difference in the output between its actual output and the desired output. And that may lead us to perform debugging. So this is where we do kind of incorporate the word bug. And for us, debugging is the process of identifying a fault given a failure. Right? So when you see a failure, oh, I expected this to return 3 and instead it returned -3. Okay, I've identified a failure, and now debugging is the process of working my way backwards through that to try to understand where is the fault that is at the root of that failure. And as I've already said, not all inputs will trigger a fault to cause an error or a failure. So, again, incorporating the cartoons, this was a suggestion from last time I taught the class, right? We want to make sure that we're doing things that drive appropriate testing and development behavior, not like this. I've actually really heard of this happening in organizations. All right, so let's take our idea here of faults and failures and errors, and let's formalize this a little bit with the Ripper fault and failure model. And so we have 4 conditions. Under this model, we have 4 conditions that are necessary for us to observe a failure. The first condition is the reachability condition, right? The location in the program that contains the fault must be reached, must be executed by some test. If no test executes the line of code that contains that fault, then clearly we'll never get a failure. Once that fault is reached, we have to have infection. Infection is when the execution of the fault results in an error, right? Some internal state, some incorrect internal state of the program. That may be an incorrect variable value. That's very common. It may also be an incorrect control flow, which if you want to put that in terms of variable, then I would say an incorrect program counter, right? Where the software has looped or branched in a way that was not the expected intended way. That infection, that internal state, has to propagate. That state has to propagate to some output or some final state, right? Somewhere where we have the opportunity to see that something has gone wrong. And finally, we have to be able to reveal, that error, right? We have to have some observation that we're making as part of our test in order to recognize that that failure has occurred. So let's look at that graphically. So I have some test, and that test has to reach the fault. When reaching the fault, the execution of the fault has to infect the program with some incorrect program state. And then that has to propagate such that the final program state is different somehow than it should have been. But now we also have to be able to reveal that state. So for example, if my test, or my test oracle, I know that's a term we haven't talked about yet, but basically just that's what we're checking, right? Those are the results that we're checking. If the results that I'm checking as a result of my test don't happen to include any of the things that were wrong, then I've infected, I've propagated, but I have not revealed the failure. If, on the other hand, the part of the program state that I'm observing does overlap with where the program state is incorrect, then I have revealed the failure. And so all four of those things have to happen for us to be able to detect a failure, and thus, by implication, determine that the software contains a fault. So traditionally, there are a number of different testing levels. So you'll commonly hear things referred to as unit testing, where we're testing each unit or each class or each method, often testing each method individually, making sure that that logic is correct. Then we can go up a level to module testing or class testing. We're making sure that this aggregation of methods is correct. People will often combine these two things under the term of unit testing. That's okay too. We can then have integration testing. In integration testing, we're looking at how those different modules interact. I've already done my unit testing. I've determined that they work well on their own, but are they talking to each other correctly? Are they making proper assumptions about what each other is doing? Right? Is this aggregation of integrated units, is this correct? Then we can perform system testing. In system testing, we're looking at the overall functionality of the system and determining whether that overall functionality meets its intended requirements. And then we have one more level. We have acceptance testing. In acceptance testing, we're basically saying, does this system do what the users need it to do? Ideally, system testing against the system's requirements will be equivalent to acceptance testing, because ideally the requirements will relate, right? If the requirements are met, then the system will be acceptable to users. However, that's not always the case. I've often, well, more than once anyway, been involved in systems that completely met their requirements. However, when they were put into use, they were not actually suitable for the users. We also have this very traditional model, this V model of systems development. And in this traditional V model, you start by doing requirements, and then you do your high-level design, and then your kind of subsystem design, your detail design, then you implement the thing you're building, and then you perform unit tests based on the implementation, and then you perform module tests based on the detailed design, then you do integration tests based on the subsystem design, then you do system tests based on the architecture design, and then you do acceptance tests based on the requirements. So each of these levels of development on the left side have a corresponding level of system verification on the right side. This is still a useful model, but it is largely outmoded by Agile methodologies that we'll talk about, I think, the next class we talk about Agile. Because this model really implies this kind of waterfall development, right? We do all our requirements, then we do all the next stage and all the next stage and all the next stage and all the next stage. And the assumption, of course, is that we have a complete understanding of the system and that the needs for this system don't change during the time that we're building it, right? So that by the time we're done, we actually got what we wanted, which in practice doesn't really work very well. So we started to talk a little bit last week about coverage criteria. And we talked about what does it mean to achieve coverage? What kind of different coverage criteria can you have? So let's take a little bit of a deeper dive. Why do we care about coverage? And for starters, even trivial programs just have too many inputs, right? You can't look at any piece of non-trivial software, or really hardly any pieces of trivial software, and say, I'm just going to test it with all the possible inputs. That's unrealistic, right? So if we had this function that takes 3 integers and computes its averages, if we're assuming we've got 32-bit integers, each variable, A, B, and C, has 4 billion possible values, so we have almost 10 to the 29th possible tests. So while that is not technically an infinite number, it may as well be, right? Because there's essentially no way that we can execute all combinations of tests, even on this pretty trivial thing. So our job as testers is to kind of look at this essentially infinite, right, practically infinite input space, and we would like to find the fewest possible inputs that will find the most problems, right? We want to do the least testing possible to find the most problems possible. And so coverage criteria will give us structured ways to do that, right? We don't necessarily need to just guess, well, let me try 1, 1, and 1. Well, what about 1, 2, and 10 million? Why'd you pick that value? I don't know. If we can set up criteria for coverage, or if we can set up coverage criteria, then we can define what our test should be to satisfy that. And so we're going to use coverage criteria to maximize the search of our input space, right? We're going to try to have inputs selected from across the whole range, even though we know we can't select them all. And we'd also like to minimize the amount of overlap in the tests, right? We don't want to repeat tests that are almost the same, because then we're doing more and more effort with a diminishing likelihood that we're going to find any problems. So there are some significant advantages to using coverage criteria to drive our testing. And first of all, it helps us maximize the bang for the buck, or in other words, maximize our testing results while minimizing the amount of time, effort, and money we're putting into our testing. It also allows us to provide traceability from software artifacts to the tests. So we can answer the question, why did you write this test, right? What is this test for? And if we have coverage criteria, then we can say, well, that test is necessary because it meets this requirement, it proves this requirement, or it proves this particular input value, right? We have a justification for each test we've written. We also have a stopping function, because one of the problems with software testing is, when are you done? And you can always come up with another test case. It's not hard to always come up with another test case. So when are you realistically done? And coverage criteria will help you with that. When I have satisfied all of the things that this particular coverage criteria calls for, then I am done. And coverage criteria is also really well supported with a lot of powerful tools. So it makes it a very practical approach. So let's talk about test requirements and test criteria. So test criteria, or a test criterion, and I'll apologize in advance because I use criteria and criterion interchangeably. And yes, I know that criterion is singular and criteria is plural, but I've been doing that for years and I can't stop myself now. So when I say one or the other, you can feel free to just fill in the correct one inside your head. So a test criterion is a collection of rules along with a process that we can use to define what our test requirements are. So a test criterion might be, for statement coverage, for example, something that a lot of people seem pretty familiar with last week. Our test criterion could be execute every statement. If we were testing against a documented list of functional requirements, our test criterion might be show that every functional requirement is satisfied. Right? I mean, that's a pretty high level thing, but that's okay. Those things lead to test requirements. And a test requirement is a specific thing that we have to do or have to prove or have to show during our testing. So for example, if our test criterion was statement coverage, execute every statement, then our test requirements would be, well, I have a requirement for each statement. So I have a requirement to execute statement number 1. I have a requirement to execute statement number 2. I have a requirement to execute statement number 99. Or each functional requirement, right? That could be a test requirement. So where do test requirements and test criteria come from? So there are many, right? Testing researchers have defined dozens, perhaps hundreds. Arguably, they're based on 4 types of structures. I'm going to say arguably because there's a whole lot of them out there and I haven't examined every one. But our textbook focuses on these 4. So we're going to stick with these 4. So our 4 types of structures, right? Input domains or input space, right? What are the possible inputs that can come into this program? Graphs. How can we make a graph-based abstraction of this program and use that graph-based abstraction to drive our testing? Logic expressions. Given the logic expressions in a program, what kind of testing do I have to do to build confidence that those logic expressions are correct? And syntax descriptions, right? Given the program syntax, what testing should I apply? So those are the 4 categories, the 4 different types of testing structures or testing criteria that we're going to talk about this semester. So there is an older view. Maybe I should have put this box up by where the other older views were. This idea of colored boxes, right? Black box testing or white box testing, sometimes called clear or glass box testing. In black box testing, we treat the system as it's just a black box, right? We can't see what's happening inside. We don't know what the internal workings are. So we're going to derive our tests from things that are external to that software. So for example, from the specifications, from the requirements, from the domain of possible inputs. That's how we might come up with test cases in black box testing. In white box testing, we have visibility into the internals of our software. And so white box testing might do things like consider what statements have been executed, or what branches have been executed, or what conditions have been executed. So when we're doing model-driven software, these distinctions are really less important. It's not really so much a case of, well, it's either black box software or it's white box software. Instead, when we're doing model-driven test design, we're asking a slightly more general question. And that question is, how are we abstracting the system in order to create tests or to identify tests? And we can abstract the system in ways that do not pay close attention to the internals of the implementation, or we can abstract the system in ways that do. And those will lead to black box or white box approaches. So we have four general kinds of test activities that we have to execute as part of building and running our tests. First, we have test design. And test design can have two parts. It can be criteria-based test design, and it can also be human-based test design. I'll talk more about these in another slide or two. We then have test automation. How are we going to take those test designs, which are kind of abstract, and turn them into something that can be executed? And then we have the actual process of executing the tests and collecting the results. And then last of all, we have the process of evaluating those results. We need to look at those test results and determine, did the software actually behave in the way that we expected? An interesting and challenging thing here is that often as a software developer, you're asked to do all four of these things. Hey, just go do the testing, right? And it's all four of these things. But these things actually require different skill sets, different background knowledge, possibly different education. So let's take a little bit of a more detailed look at each. When we're doing test design, we're coming up with test values to satisfy some coverage criteria, or perhaps satisfy some other engineering goals. This is a very technical job, right? This is very, very specific. It requires knowledge of discrete math, requires some computer science knowledge, requires some test theory knowledge. This can be very challenging and actually can really be interesting and fun. However, if you're using people to design tests and those people don't have the experience and the education and the qualifications to design tests, you're not likely to get an efficient and effective set of tests as a result. So this class, once we get to week 4 or so, will largely be about test design using criteria. We can also have human-based test design. When we're doing human-based test design, we're still accomplishing the same thing, right? We're producing test values, but instead of doing it based on some specific criteria, we're doing it based on domain knowledge, right? What does this program do? And as a domain expert in that, I have some ideas of what to look for. So for example, if we were testing a navigation system, you know, a GPS, an autopilot, Google Maps, whatever. I, as an expert in navigation system, I'm not an expert in navigation systems, but an expert in navigation systems might say, well, you know, there are a few interesting special cases here, like what happens when we cross the equator, or what happens when we cross the prime meridian, right? These are places, you know, or across the North Pole. These are places where we have kind of a discontinuous change in our latitude and longitude values. And I, as an expert in this area, I've just got a feeling that's something we should test. Because situations where we're basing tests on criteria, technical criteria, they might not understand these special situations. So designing tests in this way doesn't really require a lot of computer science, but does require a good understanding of the problem domain, right? What is this thing that we're testing? Is it a banking application? Well, I need to understand what happens when somebody, you know, writes a check that's larger than what's in their bank account. So this can also be interesting, challenging, and rewarding. But typically, this is not that interesting to software developers. right? They are focusing more on the software, are sometimes less involved with the domain that the software runs in, or the problem that the software is trying to solve. Then we have test automation. When we're doing test automation, we're taking those test values that came out of the design, and we're building those things into executable scripts, like, for example, JUnit tests. Somewhat less technical in that, yes, it requires programming, but really doesn't require a whole lot of testing theory knowledge or a whole lot of deep knowledge about what the criteria are. This can be kind of dull for test designers, right? If you specialize in the challenges of coming up with what those test designs should be, then, actually writing the JUnit tests, maybe not that interesting. But it's probably outside the skill set of people who are not software developers. So often we find as software developers and testers, we're kind of stuck with this because we're the ones that can do it. But there are some challenges. So one of the challenges is when we're designing a test, right, we have to understand what the expected output is. This sounds easy at first, but as you get into more and more sophisticated systems, it becomes more and more difficult to really understand what the expected output is. And often the software developers or the test designers don't know. Right? What happens if I put in, this value, then this value, then this value, then this value? I don't really know. We may need to get a systems engineer. We may need to get a domain expert in this topic and get them involved early so that we can understand what the expected outputs are. This is often the hardest part of actually putting tests together. Then we have test execution, right? We're going to run the tests against the software and record the results. That sounds easy. And if our tests are automated, that is easy, right? Once I've written JUnit tests, I can run them at the push of a button and I get a list of all the tests that passed and failed. That's easy. Also really tedious if the tests are not automated. If you're running on a system where you have, a user interface, graphical user interface, and there's lots of things we can do. Okay, test step number 26, pick on new and pick on user, then type in John Smith, right? Very tedious, a lot of manual labor, and very easy to make human mistakes, right? Because that's something, doing those simplistic, tedious things over and over again, that is something that we as humans are pretty bad at. Finally, we've got test evaluation, all right? I got the test results. What do they mean? Does the system actually behave the way it should? And as I said, this can be really hard. We may need to have very extensive domain knowledge to understand whether the system's output is really correct. Then there are some other testing activities that have to happen along the way, right? There's test management. Somebody's got to set the policy, organize the teams, do all the other things to keep everything running. There's test maintenance. We'll talk a bit about test maintenance across the semester. We don't want to write tests. Let me back up a second. Creating tests is hard and it's expensive. We don't want to do all that work and run our tests once and say, yay, the tests all passed, we're good. We actually want to save those tests and we want to run those tests again and again. Ideally, we'd like to run the full set of tests perhaps every night, or perhaps every time someone makes a change to the software. We'd like to rerun all the tests and make sure something hasn't been broken. The more times we rerun the test, the more value we extract out of all that work we did building them. However, software changes, right? That's our job, right? Our job as software developers is to change software. Right? That is literally what we do. But when we change software and we change its behavior, that tends to break tests, right? Tests that used to pass now fail because we intentionally changed the behavior of the software to fix it or to make it do something different or to make it do something additional. And that can add up to a lot of test maintenance effort to make sure that all of our tests remain correct as the system evolves. Then finally, we've got test documentation, right? We need to know why we developed each test. What does this test satisfy? Why do we have this test? Later, that will help us understand whether we need to keep this test. I've been involved on programs that have thousands of tests, and the tests have been around for years. And sometimes they fail and no one knows why, and no one knows whether they should care or not, because there's no documentation for the test. So this test fails. Nobody really understood what it was trying to do. That was 10 years ago anyway. Does it even matter anymore? I don't know, right? That's the problem we get into if we don't have at least some degree of test documentation. So let's talk about using model-driven test design. So when we're doing model-driven test design, we'd like to have a test designer do the theory work. And then we can have test developers, software developers, domain engineers, right, experts in the domain, do their parts, right? And they can find the specific values that we need. They can do the automation, execute the tests, and evaluate the results. So just like traditional engineering, where you might have an engineer who's going to design a bridge using various theory, right? And then that engineer is not going to get out there and pour concrete, right? That person who designed the bridge, they're not going to string cables, they're not going to pour concrete, they're going to give those plans to experts in the building of it, who are then going to go about their work. And so model-driven test design is similar. So what are the steps in model-driven test design? So for starters, we're going to start out with a software artifact. And then we have two different levels of abstraction here. In the upper gray box here, we have kind of the design abstraction level. And then in the bottom, we have the implementation level, right? So this is, the top is kind of more conceptual. The bottom is much more implementation specific. So clearly our software artifact, right, our program source code, that is an implementation, right, very specific artifact. We're going to take that artifact and we're going to do some kind of analysis on that artifact to create a model or some structure of that artifact. What is that model? Well, it could be many things, right? We could make a model of what the input space is. We could make a model of what the control flows are, right? There's lots of different analyses we could do to come up with lots of different models. But the process, right, at a high level, the process is basically the same. We're taking the software artifact, analyzing it, and turning it into an abstracted model of what that software is. Then we're going to apply some test criterion. And applying that test criterion is going to give us a set of test requirements. These are the things that I have to test, or that I have to show in order to, that I have to demonstrate in order to show that the system is correct. I may also do, like we said, human-based analysis, right? So I'll do a domain analysis. I'll get an expert in this topic in here, and they will come up with test requirements based on their understanding of the domain. So what are some of the special cases? What are some of the problems that have happened before in systems like this that we want to make sure don't happen again? And so they'll come up with their own set of test requirements. We'll refine those test requirements and merge them together to create our test specifications. We're going to use those test specifications to generate test inputs. Now we've kind of crossed back over into the implementation abstraction level, because our test inputs are specific values, right? North 37 degrees, 49.265 minutes, you know, west 77 degrees, whatever, right? A specific set of test values. Then we're going to come up with, well, what are the prefix things we need to do? In other words, what do I need to do to put the system into a state such that it can accept these test values? And then what do I need to do as postfix? What do I need to do to get the system to process it and to then recover to a normal state? And finally, what are our expected outputs? And we're going to roll all that together into a set of specific test cases. Then we're going to automate those test cases and create some test scripts. In this class, for the most part, those test scripts will be JUnit tests. Then we're going to execute those test scripts and collect the test results. And then finally, we're going to evaluate the test results and determine whether the test has passed or failed. Now, many times, if we have a good understanding of our expected outputs, we can build the evaluation into the automation so that when the test scripts run, the test results themselves will tell us whether the test passed or failed. Other times we have more complex tests that will maybe generate a whole batch of data, and we'll have to do some data analysis or some data reduction to understand whether that test passed. So let's take another look at this, but let's group this into a little bit of higher level activities. So we have a test design activity. And in the test design activity, we're doing the analysis to make the model. We're applying criteria to generate test requirements, and we're refining those test requirements to create test specifications. Then we have a test automation activity. We're going to determine what the input values are, we're going to create the test cases, and we're going to automate them into test scripts. Then we have a test execution activity, right? Run the tests, get the results. And finally, we have a test evaluation activity, determine whether the tests passed or failed. So that's kind of our high-level view of model-driven test design. And so certainly, the further we can raise the level of abstraction, the easier it is to design our tests. And this section in test design, next class, I believe we talk about test automation. The next two classes, we talk about agile methods and test automation. After that, we jump over and basically spend the rest of the semester up here in the test design activity, mostly looking at how do we apply criteria to create test requirements. All right, so let's look at an example. Here's our software artifact that we want to test. The software artifact index of, given an object, this is actually a method, right? This index of is a method on a list, right? So it's a method of a collection. We're going to pass in an object, and this method is going to scan through its list and determine whether this object exists in the list. And if it does, it's going to return the index in the list of this object. And if it doesn't, then it'll return -1. So let's create a model of this artifact. And so one type of model that we can create, a very useful type, is a control flow graph. I'm going to presume that most of you, hopefully all of you, are at least somewhat familiar with control flow graphs. All we've really done here is modeled how can execution flow through this code. And so we have these nodes where a node will contain one or more lines of software, and we have these edges that connect things. So when we enter this piece of software, the first thing that will happen is that I is initialized to 1. That's the initialization portion of the for statement. Then we do a check to determine whether I is less than or equal to list.size, right? That's the evaluation part of the for statement. If it's true, and I didn't label these branches true or false, although I probably should have. If it's true, then we branch down to this node where we look at the if statement, if list.get.equals O. I didn't write it all out here because there's not enough room. If that's true, then we return I. If it's false, then we go back up to the loop, we increment I, and go back again to check whether I is less than or equal to size. Eventually, if I is equal to size, then we'll bail out of the loop and we'll return -1. So this is actually, this one's true and that's false, and then this one's true and that's false. So they're a little backwards, really calling out for noting these with true and false. But there's basically our control flow graph representation of this piece of software. So what can we do with that control flow graph? Well, given that control flow graph, we can identify a few things. We have an initial node. This is where execution always begins. And we have some final nodes or terminal nodes. This is where execution can end. And it can end with returning -1, or it can end with returning I. And then our graph has a bunch of edges in it, right? All of these graph edges, all of these arrows that connect the nodes. So there's an edge from 1 to 2, there's an edge from 2 to 3, from 2 to 4, etc. So that gives us some things, right? Some attributes of this abstraction that we could test. There's also a good tool for graph coverage. As we get into graph coverage, I'll mention this again, but this website actually has some pretty cool little tools on it done by a previous grad student. So let's make some test requirements. Let's say that we set our criteria to be edge coverage. So our criteria is edge coverage, which means I have to execute every edge in the graph. Okay, if that's my criteria, then I can come up with 6 requirements. The requirements are simply all the edges in the graph. So 1, 2, 2, 3, 2, 4, 4, 5, 4, 6, and 6, 2. Those are my test requirements. Then I need to come up with some potential test paths. Okay, if those are my test requirements, how can I manipulate, or how can I work my way through this control flow graph to satisfy those requirements? Well, I could have 2 test paths. I could have 1, 2, 3, and that will satisfy edge 1, 2 and edge 2, 3. Well, that leaves a lot of edges unsatisfied, so I need another test path through the graph, but I could go 1, 2, 4, 6, back around to 2, 4, 5. And that would be a path through the graph that would execute all the remaining edges. It executes 1, 2, but then also 2, 4, 4, 5, 4, 6, and 6, 2. So those 2 test paths will satisfy all of my test requirements. Now, I need to find some values. What values could I actually use in testing to execute those paths? Let's take a look. So if I want to execute test path 1, 2, 3, then I could set an empty list, and I could set anything really for O, the object I'm looking for. The simplest thing to do would be to set it to null. And if I did that, then the execution will come in, it'll set I to 1, or excuse me, it'll set I to 0. It'll come, it'll determine, is 0 less than list.size? No, because list.size is 0. So I is equal to list.size. So it'll come over here, return -1, satisfying, executing this test path. If I want to execute this other test path, 1, 2, 4, 6, 2, 4, 5, then I have to think about, all right, what are my possible inputs that could execute this? Well, I could set my list to contain 1 and 2. Right? Intuitively, I kind of feel like I'm going to need a list with at least 2 things because I have to go around this loop. And if I have to go around the loop, then I need at least 2 things in my list. So we'll make a simple list. We'll set it to 1, 2. Then I'll ask it to find 2 in the list. And so execution will come in, set I to 0. Is I less than size? Yes, it is. Is the 0th element of the list equal to 2? No, it's not. So we'll increment I, we'll come back around. Is I less than size? Yes, it is. Is the 1th, the list element indexed by 1, is that equal to the object we're looking for? Yes, it is. And so then we'll come down to 5 and we'll return I. So those set of inputs will execute this test path. So now I've made a model, right? This control flow graph. I've applied a criterion, edge coverage. I've used that criterion to identify what my test requirements are, the set of edges. I've then analyzed those test requirements and come up with 2 test paths. And then I've looked at the code and identified specific test inputs that will execute those test paths. Next, I'd go on to test implementation, right? I need to implement the tests. I need to make my test scripts. Again, in this case, probably JUnit tests. We'll look at that in future classes. We're not going to dig into that tonight. All right, that takes us to the end of the lecture section for tonight. So we're, not quite an hour in, so we're actually doing pretty good here. Questions, comments, or discussion on tonight's content? All right, then here's what we'll do. Sorry, Kyle, do you have a question coming? I saw you moving the boom mic.
No, I don't. Sorry.
Okay. All right. Here's what we'll do. We'll go into our break time. We're actually doing pretty good tonight, so let me stretch this a little bit. We'll make it coming back at 5:40. So 13 minutes, soon to be 12 minutes from now. So an extra 2 or 3 minutes for you. We'll start back at 5:40. We'll break up into our groups. While you're you can use that extra 2 minutes to go to the content class, the course content site, grab the exercises that are there, because it will be very handy for you to grab the week 2 exercises and have that handy as we go into our class exercises. All right, so see you in 12 minutes at 5:40. All right, so we've got a couple different exercise rounds. We're going to do this one round at a time. So we'll go. We'll talk about one problem. We'll break up into our groups. We'll all come back. Each group can discuss one part of this, one part of one piece of the answer, and then we'll go into the next one. Go back into groups again. All right. So we're based on the book here. Chapter 1, exercises 5 and 7 we're going to look at. You don't have to have the book with you because I've got the code here in the slides. So given the code, we want to identify what is the fault. And then if possible, identify a test case that does not execute, does not reach the fault, right? So we're talking about the Ripper model here. So we want to find a test case, right? A specific set of input values that does not reach the fault. And then we'd like to identify a test case that reaches the fault, but does not cause an error, right? So no incorrect internal state. And then we'd like to identify, if we can, a test case that reaches the fault, results in an error, but not a failure, right? And identify what the initial error state is. And then finally, we'd like to identify a test case that reaches the fault, causes an error, and causes a failure. Right? And so here is our first bit of software, right? Our first question here. So we've got find last. Find last is going to take an array and it's going to look for a particular value in that array, and it's going to tell us the last index where that was found. All right, so I'm going to break us up into our groups. This might be a little slow here because it looks like I'm guessing that a lot of people are not logging on to Zoom with their GMU email. And so I've pre-programmed these groups based on your GMU email. I'll send an email out later. If you're not using your GMU email, reply to me with what email you are using to log into Zoom so that I can kind of automate the group setup. So it's going to take me 2 or 3 minutes to get everybody into their groups because I'm going to have to go down the list of names and send you all there. So the first thing for you to do in your group is to identify who's going to lead the group today, because there are two active roles. Somebody has to lead the group. Normally, that person will share their screen on Zoom, right? And that's all I mean by lead the group, right? You're the one sharing, you're the one coordinating everybody, you're the one writing down what people are saying, right? You're kind of collecting the answer. And then someone will present your part of the results. It doesn't need to be the same person. There are previous classes have used a number of different tools. People have used just on Zoom, people have done cooperative stuff over Office. They've used other tools as well. Each group, you guys can decide however you want to run the group. So again, like I said, there's going to be one person who's kind of managing the group, and then one person, the same person or a different person, who's going to be reporting on what the results are. Yep, Google Doc. That's a lot of people have used Google Doc. That's a great solution. There was one really cool one that somebody had last fall. Unfortunately, I can't remember what it was. I may have a note somewhere. They were able to like draw stuff, and it was really neat. It was a great collaboration tool. But I'm not going to dictate that. Each group can use whatever you're comfortable with. So, any questions before we go off into groups? All right, I'm going to send you on your way then. There's probably about 15 of you who are going to be in your group immediately, and then other people are going to trickle in as I kind of go through the list and get you all sent in there. So bear with me for a couple minutes while I get you all sent off to your groups, and then I'll start just kind of hopping around and visiting in on each group. All right, see you in a few minutes. All right, so welcome back, everybody. I realized that after I'd sent you all, I realized that I hadn't set the timer or hadn't changed the timer. So that was actually a little shorter than I'd intended it to be. I'll set a little bit of a longer timer next time. I'm a little bit out of practice on this, just like you all are. So let's see. Let's go to the Hufflepuff team first. And when looking at find last, what did you find as the fault?
So as far as we could tell, the fault was the terminal condition for the for loop. I think it should, or we think it should be, I can't remember let me pull it up. But the indexing variable, it's I greater than 0. It should be I greater than or equal to 0, or I greater than -1.
Okay, great. Yes, very good. So this loop basically terminates early. So it should be greater than or equal to 0. Yep, so it'll never check.
I did have a nitpick on that.
Sure, go ahead.
The null pointer exception, there's no validation or check in the method. Should we assume that we just have like an if null throw null pointer exception?
So if x is null, then when it tries to dereference x, when it calls x.length, that will cause a null pointer exception to be thrown.
I see. So not explicitly mentioned, but it's there.
Yes,
part of the language.
Right, that'll be a behavior of how the Java language works.
So we cannot consider that as a fault?
That is not a fault. Okay. Right, because that's part of the expectations, right? The expectations are kind of listed here at the top. It'll throw a null pointer exception if x is null. So that is part of the expectation.
I think in terms of the cases with null fault, I think it was Jesse who caught this, but you actually need to throw a null pointer exception to avoid hitting the fault, because anytime you check I, you'll be hitting the fault. So the no fault case is the x equals null, I think. That's what we determined.
All right, so that's interesting. Let me share my screen here. All right, so as you said, the loop terminates early. If I equals 1, how do we avoid hitting the fault, right? The fault is highlighted here. Is there a test case that doesn't execute the fault? And yeah, providing null to X will cause it to exit early on a null pointer exception and not do this. If there was a way for us to execute the loop and leave on the first execution, then that would also, no, it wouldn't. Never mind. That wouldn't
Because
exit.
you know that, yeah, that
Because it does the initialization and then the comparison right away before it does the loop body. So you are right. The only way for us to not reach the fault is to give a null value for X so that it leaves on a null pointer exception.
Yeah, that didn't occur to me that it does that comparison unless it fails. So I would have gotten that wrong on my own.
Okay, great. Well, that's why we work in groups. All right, so let's go to the Gryffindor. The Gryffindors next. So Gryffindors, do you have a test case for us that doesn't result in an error?
Hi, it's Christina. I also don't have headphones on because I got a new piercing and I'm trying to avoid that, but I'm from Gryffindor. A test case that we came up with was an array that contained 1, 2, 3 because the index of the index 1 has the 2, which is y equals 2. So it'll return a true statement.
Okay, so an array of 1, 2, 3, right? So you're setting X to 1, 2, 3, and you're setting Y to 2.
Yes.
Okay, great. Not exactly my test case, but of course there's no reason to expect that anyone would come up with exactly my test case. But you're right, because really all we need is any array where Y appears after the first element of X. Another possible thing that will not result in an error would be X being empty. Because if X is empty, but not null, just empty, then we'll hit the fault, but the I is greater than 0 will be false, and so we'll just return -1. Great, thank you. Excuse me. So let's go to the Muggles next. And so Muggles, do you have an error that does not result in a failure?
So we came up with whenever y is not in X.
Whenever Y is not in X, we'll have an error. Why do we have an error?
I'm not sure. Sorry.
It's okay. Other Muggles, you can chime in.
I think because it will, jump out when I is equal to 0. It will not check whether the element of index 0 is equals to y, but because y is out of the X, they will finally return the -1 as the correct output.
Yes. I think I agree with what you said. Let me rephrase what I think you just said. And let me rephrase it just a little bit differently in terms of what the error is, right? And so the error is a control flow error because we left the loop early, right? We didn't check the 0th element. We checked the last element. We checked this, for example, we checked the 3rd, then we checked the 2nd, but we didn't check the first, well, I guess I should say the 0th. We didn't check the 0th element of the array. So it's an error because the control flow isn't what we expected, but the returned value is what we expected. So There you go. If y is not in x, then the final value of I is an error, or at least an error occurs, but the final value, the final value of I, the index, is incorrect. But it's not a failure because the returned value is correct. And then let's see, Ravenclaws, you're up next. Can you give us a failure?
Any array where y is the zeroth in the zeroth index. So we just wrote x is 0, comma 1, and then y is 0.
All right, any array where y is the 0th element. Yeah, there you go, exactly. Although guess I'll clarify that a little bit in your answer as well as mine, and say only in the 0th or first element, right? Because if it was 1, 0, 1 and you asked it to find 1, then that would not be a failure because it would return 2. But as long as y is the first element in the array and only the first element in the array, then that will generate a failure. All right, nicely done. So that's going to take us to part 2 here. We'll break up into our groups again. It should be faster and easier this time because I should just be able to send y'all back where you were. I'm also going to set the timer to give just a little bit more time. So here we're looking for the last 0. Excuse me. We're looking for the last 0 given an array. We want to find the index of the last 0 in an array. We'll return -1 if there is no 0 in the array. Same rules on null pointer exception. If x is null, then it throws null pointer exception. That is the expected behavior, so that is not an error or a fault. All right, ready to go?
Yeah.
All right, I got to remember how to do this. Where's my timer? Boy, you know, you take a semester off and you just forget everything. That's why I never took a semester off when I was in school, because I was pretty sure I wouldn't go back. Options, there we go. All right, 15 minutes, that sounds good. So let's go. All right, so let's pick back up with this. Let me share my screen again here. All right, and we're gonna jump over to the Slytherins now. So Slytherins, tell us about the fault.
This is Blake speaking. So we decided that the fault is kind of the 3 statements in the definition of the for loop. So initializing I, the Boolean condition I is less than x.length and I++, the all long.
Okay, so generally speaking, what's wrong with that?
So it's traversing left to right instead of right to left.
Yeah, so in essence, this is the very definition of the function first 0, not last 0. Okay, great. Good, so your identified fault, the loop returns the first index of 0, and probably it should count down instead, right? It should initialize to x.length -1, compare that I is greater than or equal to 0, and do an I minus minus. Now, this is an interesting case, as I was talking about with a couple of the teams, because there are other possible solutions, right? There are other possible fixes. And if we talk about there being other possible fixes, that implies that there are other possible faults. So another fix that I could make here would be to add a line before the for statement that says, for example, int answer equals -1. and then replace this return I with answer equals I, and then return answer, right? So that we're still going forward, but we're tracking the most recent index found, and then we're returning it. So that is an alternate implementation. But if I decided that was my, I guess I'll say my reference implementation, the implementation that I have in my mind, then that implies that this for loop is fine. And the fault is that there's no other variable and we're returning I instead of saving it. I don't think that's a great solution. I think that just reversing the for loop, which is probably the obvious thing to do, right? That's probably the better solution. So it's most reasonable to say that the fault is in the for loop. So while we're here with you, Slytherins, do you have a test case that does not execute the fault?
A test case that does not execute the fault should not execute the for loop. So if the array is null, because I'll throw a null pointer.
Okay. So if the array is null, it'll throw a null pointer exception, but does it execute the fault? Well, if we consider the whole for loop to be the fault, then anything that enters this function is going to hit int I equals 0. So I would argue that there's no inputs that don't execute the fault, because all possible inputs will execute the loop initialization. If we said that, well, only if we had some other example where only the increment part is wrong, the rest of it's fine, then you could say, well, if I got through the loop once, right, if I got into the loop and then returned, then that would be fine. I wouldn't execute the fault. But here, since the initialization is wrong, I really can't get around it. All right, so let's jump back to, let's come back around to the Hufflepuffs again. So Hufflepuffs, do you have a test case that does not result in an error?
So an array of 0, 1, I believe. So anything with just 1, 0 in it would, wait, or does not result, wait, actually does not result in an error.
Right, does not result in an error. There's no error of internal, there's no, no incorrect internal state.
Oh, I think, no, I think our decision was it has to be an array of just one element, that being a 0.
Okay, an array of one element with a 0. So if it's one element, then we initialize I to 0. So that's actually okay. And then if it was 0, then we'd return I, we'd return the 0. So an element of one array, an array of one element, excuse me, looks like an array of one element would be okay. We are going to test again, is I less than length. We've certainly executed the fault, but I isn't really wrong. I is what we'd expect it to be. And the control flow is what we'd expect it to be. My example is if X were null or X had a length of 0. But also, you can make the legitimate argument like you've made that if it's a length of 1, then that's actually going to be okay too. All right, good job. And so Gryffindors, do we have any test inputs that will cause an error but does not result in a failure?
If the array has only 1 0 in it?
If it has 1 0 in it, yeah, right. Any value for X in which 0 appears no more than 1. So it could be not at all, or it could be only 1. So then we'll have an error state because we're counting the wrong way, right? So our our value for I is incorrect, but we'll either return -1 if there was no 0, or we'll return the right index if there was only 1 0. Great. Good job. Thank you. And then that was Gryffindor. So we'll go back over to Muggles. Do you have a case for us that causes a failure?
I would say the current case works where the array is 0, 1, 0, or in any case where 0 appears twice.
All right, any
Or more
case
than
where
once.
0 appears, yeah, 0 appears twice, or more generally, more than once in X. Great. All right, so we've actually got 2 more, but really we have time, I think, for 1 more. We're 20 of now, so yeah, I'll do another 15 minutes here. That'll give us 5 or 6 minutes to outbrief and still be done more or less at 7, which is always my target. All right, so we're going to do exercise 5, part 3, count positive. Read the comments carefully, because that will help you determine what the fault is. So I'm going to send you back in, and we'll see you back here when we're done. The group that I just left probably had the best quote of the course, which is, "I'm literally going to cry right now because I just learned that," fill in blank here. All right, so let's look at exercise 5, part 3. A lot of people, maybe most people, did part 4. Maybe we'll just really quick zip over that. I don't think anybody got to the last part, and we won't talk about that tonight. All right, so I don't really remember where we left off, but let's arbitrarily pick up with Ravenclaws. And so Ravenclaws, let me share this again here. Looking at count positive, what did you find the fault to be?
Hello. Okay, sorry. Go ahead.
Okay. The greater than or equals to 0.
Greater than or equal to 0, and what should it have been?
Greater than.
Just greater than. Okay, right? Because this algorithm, as it's written, counts zeros as positive, and as I subtly hinted to you about the comments, there's a helpful note up here that says 0 is not considered positive. When I first saw this example, I was like, no, that's not right. 0 is positive. Let me go look that up. And actually, I got conflicting answers depending on where I looked. Everyone agrees that 0 is non-negative, but whether 0 is positive or not is kind of an open question depending on who you ask. All right, so sticking with the Ravenclaws for the moment, do you have a test case that does not execute the fault?
A null array.
All right, if X is null, or if it has a length of 0, that'll work as well, because then it will skip over the body of the loop. Great. So let's go to Slytherins. And Slytherins, do you have a test case that does not result in an error? Right, so no error of internal state.
Yeah, so it could just be an array with the only element being 1, but in general, it's any array that does not include 0.
Any array that does not include 0. Excellent. And while we've got you here, we may as well just stay here. Do you have an error that does not result? Do you have an input that results in an error, but not a failure?
We said no because the external like variable that you see as count is the one that has the that is an error. So it wouldn't be possible to have an error, but no.
Great. Every input that causes an error causes a failure. Because if when you have errors of control flow, often, or at least sometimes, an error of control flow might not cause a failure. An error of a variable setting is more likely to cause a failure. It's not impossible that you could have other code in here later that ignores count or does something with count that makes the error state go away. But here it's pretty hard because you increment count when you didn't really want to, and then what's the next thing you do? You return it. So not much getting around that. And then a failure is pretty easy, right? Any value of the array that includes a 0 that's going to result in a failure. So let's take a quick discussion here, because I know a lot of people did it, so just arbitrarily call it out. We won't go group by group, but looking at odd or pause, what's our fault?
So I feel like you're a little tricky with this one because so it's a modular arithmetic. It should, according to the Java library, I did a check on an online Java compiler. A negative positive number modulo 2 will be equal to -1.
Yep. Java's mod operator takes the sign of the quotient. The Java language developers consider this a feature. The rest of the world considers this a bug. It's peculiar, and I'm not aware of any other languages that work this way. There probably, there may well be others, but I'm mostly a Java and C++ developer, and with some Python, and Python doesn't do this, and C and C++ sure don't do it. So that's the fault. Do we have a test case that doesn't execute the fault?
X is empty.
If it's null.
Okay, if X is null or if it's empty, then we won't execute that. That sounds good to me, right? So it's null or it has a length of 0. Great. Do we have a test case that doesn't result in an error? I see it's 7 o'clock, so I'll make this quick because I do like to get you out at 7. So any values for X that only contain non-negative or even negative numbers, it'll execute the fault, but it won't cause an error. Anything that does cause an error also causes a failure for the same reason as last time. By the time we get to the point where we increment count and then return it, there's no way to go back and fix count. And a failure, pretty straightforward, any value of X that includes a negative odd number. Our last one was rather more complicated. I encourage you to at least take a look at this. As of right now, the version with the answers should be posted. The version of the exercises with the answers should be posted on Blackboard. You should at least take a look at this and understand it. The quiz will be based on examples like this, but not examples like this one because this is too complicated. The quiz will be more like, these other earlier examples that we looked at. Any questions before we break for tonight?
Do we have to submit these in-class assignments?
No.
Anyway.
The in-class assignments are not graded. This is just your opportunity to get some experience, to work through some things, and to build your expertise for the quiz.
Okay, so we're not submitting anything.
Don't need to submit anything here. Nope.
All right. Thank you, sir.
All
just
right,
another new question. This
yeah,
week's
sure.
quiz, is it based on this week's lecture or last week's lecture?
This week's quiz is based on this week's lecture.
Perfect.
So the quiz opens right now, and it's due Thursday night, and the topics on this quiz are things we talked about tonight.
Got it. Thank you.
You're welcome. All right. Well, thanks all for coming out, and see you next week. And drop me an email or post something in the chat if you want to talk something over. And otherwise, I'll see you next week. Actually, I will not see you next week. Next week is Labor Day holiday. See you in 2 weeks.